Let's look at distributions of functions of a random variable. For example, 2015 Society of Actuaries Sample Exam P, Problem 71. The time t that a manufacturing system is out of operation has cumulative distribution function, sometimes we call this CDF, f of t equals 1 minus 2 over t squared for t greater than 2, and 0 otherwise. The resulting cost of the company is y equals t squared. Let g be the density function for y. Determine g of y for y greater than 4. Okay, in this problem, you're told the PDF, actually CDF, but you can take the derivative to find the PDF, of a variable t. And you were asked to find the PDF of a function of this variable, t squared. So again, look again. You were told the CDF for t. You can use that to find the PDF for t. And you're asked to find the CDF, or actually the PDF, sorry, for t squared. So here's how we solve such problems. Suppose you're told the PDF of a variable x, and you're asked to find the PDF of a function of this variable y. So y is a function of x. Let x be a continuous random variable with PDF f of x. So again, as usual, x has PDF f of x between a and b. And y is, let's say, u of x, where u of x is continuous and monotonic. Then the PDF of y is f of u inverse of x times du inverse, derivative of u inverse with respect to y, for y between u of a and u of b. So, I mean, this makes sense because if y equals u of x, then x equals u inverse of y. So it seems reasonable that f of x, that if f of x is the PDF, if f of x is the PDF for x, then f of u inverse of y would be the PDF for y. And you just need to remember to throw in this absolute value of du inverse dy factor. We are told the CDF, so we can find the PDF by differentiating. The CDF, f of t, is 1 minus 2 over t squared. That's 1 minus 4 over t squared. In other words, 1 minus 4t to the negative 2. So the PDF is just the derivative. F of t is capital F prime of t, and that's going to be 8t to the negative 3. If t has PDF, f of t equals 8t to the negative 3 for t greater than 2, then y equals t squared has PDF. Okay, again, we've got that factor, f of u inverse of y times the derivative of u inverse with respect to y. Here, y equals u of t is t squared, so t is u inverse of y. In other words, that's going to be square root y. And the derivative of u inverse with respect to y is just the derivative of square root y. And the derivative of square root y is 1 over 2y. So the PDF is going to be f of u inverse of y times the derivative of u inverse dy. In other words, it's f of square root y, because that's u inverse of y, times the derivative of u inverse, and that's 1 over 2y. Okay, so we get 8 square root of y to the negative 3, because if f of t is 8t to the negative 3, then f of square root y is going to be 8 square root y to the negative 3. And then we have this 1 over 2 root y factor as well. We can take away the absolute value signs because it has to be positive. That's, in other words, 8 over the square root of y cubed times 1 over 2 root y, which the 8 and the 2 cancel. You're left with 4 over square root y to the fourth. In other words, 4 over y squared. So that answer is A, 4 over y squared. Here's another example. Let x have PDF f of x equals 2x for x between 0 and 1. Let y equal negative 4x plus 3. Find the PDF of y. So note that this function u of x equals 4x plus 3 is continuous and monotonic. It's decreasing. It's got to be, that function u of x has to be continuous and monotonic for this to work. Y is negative 4x plus 3. We need to find the inverse. Y minus 3 equals negative 4x. Y minus 3 over negative 4 equals x. So u inverse of y would be 3/4 minus y over 4. Again, x is y minus 3 over negative 4. You can write that as y over negative 4 plus 3/4. And indeed, we do that on the other side. U inverse of y equals 3/4 minus y over 4. And the PDF of y is f of u inverse of y times the derivative of u inverse with respect to y. So that's f of 3/4 minus y over 4, because that's what u inverse of y is. You just plug that in here. times the derivative of u inverse with respect to y. Well, look at this. What's the derivative of this with respect to y? It's just going to be negative a fourth, so that accounts for this factor here. So we get f of 3/4 minus y over 4 times negative 1/4. Based on how we've defined f, that's going to be, well, actually, that works out to be 2 times 3 over 4 minus y over 4 times 1/4. In other words, it's that's because of how we define f again. F of x is 2x. So that's 3/4 minus y over 4 times a half, or in other words, 3/8 minus y over 8. And that's for y. Since x runs between 0 and 1, y is going to run between u of 0 and u of 1. U of 0 is negative 4, 0 plus 3, which is 3. And u of 1 is negative 4 times 1 plus 3, in other words, negative 1. So the PDF is 3/8 minus y over 8, and that's for x for y between negative 1 and 3. We'll call this PDF g of y, not f of y, because we've already defined f of y differently. That would be confusing. Believe me, this is already confusing enough. Find the CDF of y in the above problem. Okay, we're going to call this CDF g of y, not f of y, because we've already defined f differently. Note that the lower limit of integration is negative 1 because the values of y are between negative 1 and 3. So again, to find g of y, capital G of y, the CDF, we integrate the PDF, little g. So capital G of y is the integral from negative 1 to y of g of t. In other words, it's going to be the integral from negative 1 to y of 3/8 minus t over 8 dt. Integrate that, and we get 3t over 8 minus t squared over 16. As t goes from negative 1 to y. Plug in y, you get 3y over 8 minus y squared over 16. Plug in 1, and you get this expression. So this is going to simplify to 3y over 8 minus y squared over 16 minus this expression. Again, negative 3/8 minus 1/16. So, you can find a common denominator, negative 6/16. This ends up being 3y over 8 minus y squared over 16 minus negative 7/16. Or in other words, 3y over 8 minus y squared over 16 plus 7/16. We can use a similar concept to simulate a random sample from a particular distribution. This is cool application of this. Suppose x is a continuous random variable with CDF, capital F of x, for x between a and b. We can simulate a random sample of values of x from this particular distribution. Okay, let y equal f of x. Then x is going to be f inverse of y. Now the domain of f of x, that's the values of x between a and b. And the range of f of x, again, it's a CDF, so the range of f of x is the numbers between 0 and 1, because that tells you how much area is to the right of x, or actually to the left of x. Conversely, the domain of f inverse of y will be the numbers between 0 and 1, and the range of f inverse of y will be the values of x from a to b, because you reverse it. In other words, the domain of f of x is going to be the range of f inverse of y, and vice versa. So in other words, the domain of f inverse of y is numbers between 0 and 1, and the range is just the values of x from a to b. So if you plug into f inverse of y random values of y from 0 to 1, that's the domain, we'll obtain random values of x. And the random values of y from 0 to 1, you can just obtain from charts of real random numbers. For instance, table 9 on page 669 of our textbook is a table of random numbers from the interval from 0 to 1. So for example, let x have PDF f of x equals x over 2. Simulate a random sample of 10 values chosen from this distribution. First, we need to find the CDF, capital F of x. Capital F is just the antiderivative from 0 to x, f of t to t, the integral. It's the integral from 0 to x of t over 2 dt, which is t squared over 2 from 0 to x. Plug in x, and we get x squared over 4. Plug in 0, and we get nothing, so we get x squared over 4. So y equals capital F of x equals x squared over 4. That's our CDF. Let's find f inverse. X squared equals 4y. So x equals square root of 4y. In other words, 2 square root y. So that's our f inverse, the inverse of the CDF, 2 root y. Okay, now we plug in 10 values from a random number chart to obtain a simulation of 10 random values of x. Let's take the first 10 values from the random number chart in our book. So 0.3407, 0.5044, etc. We just plug these into f inverse of y, in other words, 2 square root y. So when you plug in y equals 0.3407, 2 square root y is going to be 1.16739, and etc. You just plug in these values of y into this formula, and you get this. And again, this is a simulation of 10 random values of x, where f has that PDF that we talked about earlier. Even the TI can do this. What you would do is type in 2 square root rand, because again, all we're doing is plugging in random numbers into 2 square root x, or 2 square root y, and plus enter 10 times, because rand produces a random number between 0 and 1, and is available by choosing math, and then PRB.